Hello everyone, this is the part 3 of the introduction of the MOOC, and we will be having a look at the ERIGrid 2 educational and training tools that developed the past few years. My name is Alexis Kondou and I have been the work package leader of Educational Activities Work Package, and I'm a PhD candidate in National Technical University of Athens in Greece. In the frame of ERIGrid, more than 45 educational material and activities have been delivered. Some of the material concern webinars, courses in learning tools, lab modules, virtual labs, videos, etc. And the activities are related to activities in high schools, activities for the general audience, and also participation in panel sessions and other research activities regarding education. You can find more information, and most of the developed material is available on the online research center that is hosted in the project's website. You can find the link below. So in the online repository at the project's web page, you can find, as we said, the education tab, where you will find all the developed material classified in those 5 categories: co-simulation, real-time simulation, modern power system validation, remote ICT labs, and microgrids and others. Complementary to the educational material, ERIGrid 2 offers free access to 10 virtual facilities. You can access and start using the free virtual services right away, taking the following points into account. First, the provided virtual data services and resources are openly and freely available under open access licenses, so you do not need to request any access or any permission to access those services. So the access is quite quick, easy, and you can access whenever you are available and at any point and time of the day. So there is limited administrative obstacles regarding that aspect, and users can try the provided services without any obligation, like providing a report or anything else. The drawback on that is that no individual support or supervision is offered. However, there is available a forum, and you can make specific questions to the owners of the virtual facilities, and the response will be quite immediate and you will be provided with help. More information you can find in this link below. Now we will proceed with some examples of the developed educational tools. The first tool, named Smart Grid Applications, leveraging machine learning principles in RStudio, was developed by University of Cyprus. And this tool was developed to demonstrate the use of data-driven machine learning principles for the implementation of solar-specific smart grid applications, digital twin predictive performance models, and solar generation forecasting. There are 2 models or scripts. Let's say one which is a solar PV system predictive model, and one solar PV generation day-ahead forecasting model. More information and the access to tool you can find in ERIGrid 2 webpage, as well as in the GitHub. So all the tools are publicly available and free access. Next is an open source load flow tool in Python, which was developed by the Center for Renewable Energy Sources and Saving in Greece. This tool is a load flow tool that it is scripted, it is programmed in Python, and was developed for load flow analysis of power systems. The package includes data for an example, as well as the implementation and the sample example in MATLAB Simulink for comparison. As you can see in this slide, the four scripts for the code implementation are provided, and also the input data to those scripts out of this format. And more information, again, you can find in the repository in GitHub, also in the ERIGrid 2 webpage. CRES also developed an energy analysis tools that allows techno-economic analysis of microgrids and islanded power systems. Flexi, as the program is called, is for the early simulation of a small electrical system, like an electrical system of a small island or a small autonomous community. Moving in similar applications, National Technical University of Athens, or ICCS, has developed two Jupyter interactive notebooks in the frame of ERIGrid for power flow calculation in transmission networks using MATLAB and Python programming languages. In these notebooks, each step of the power flow solution is analytically described, providing insight into the theory, and the source code is matched to the theory, and the results are being displayed below the code. So it is very useful for laboratory education and for students, let's say, or people who are not very experienced, and they can correlate very easily the theoretical part with the implementation of the code. Another interesting application is the virtual lab that provides an overview of the SCADA system of the University of Cyprus microgrid and demonstrates to users the smart grid concepts of real-time observability and supervision at microgrid frequencies using a network of smart meters, programmable automation controllers, streaming data from grid assets to cloud. A user-friendly cloud-based supervisory dashboard has been developed in order to stream the real-time measurements from the UCY's microgrid. Now we will have a look to some VA services examples. In the frame of the project, a multi-energy network simulation benchmark was developed. The benchmark specification documents as well as two complete reference implementations are provided online. Only a web browser is required to run the simulation and analyze the results. So no local installation of simulation software is needed, and there you can find everything that is needed to run your examples. The second VA is called Smartest Sim Lab. It's developed by AAT and provides a comprehensive computing cluster infrastructure with different simulation tools for analyzing complex smart grid and smart energy system scenarios. More specifically, the Smartest Sim Lab is a simulation as a service platform that provides a web-based co-simulation platform based on Mosaic, Docker, Jupyter Lab, and Jupyter Hub. More information can be found in the link below. The third example is the RSC's DirtyF DAS platform that provides access to historical and real-time data for a real low-voltage microgrid at RSC's Distributed Energy Resources Test Facility. The infrastructure is composed by a time series database and an object storage that is accessible through a web interface that allows to explore the information at component and system level. The infrastructure is cloud-oriented with a web application, and it can be found at the link that you can find in this slide. The last example of this presentation is the OpenAFPM. It was developed by ICCS, and it is, let's say, a toolset, an online design toolset for locally manufactured small wind turbines. This toolset allows the modeling and the design of axial flux permanent magnet generators for wind electric systems with the use of the open source finite element analysis software. More specifically, there are three tools. The first one, the Magnet FPM, allows the design of a generator for a specific set of rotor blades and a specific set of permanent magnet dimensions. The next one, the user AFPM, can be used for validating the performance of a specific generator geometry by performing a finite element analysis using FEM. And the last one, OptiAFPN, uses the particle swarm optimization to optimize the dimension of the permanent magnets used in the generator design for a specific set of rotor blades while minimizing the generator's cost and mass and maximizing its efficiency. More information about this virtual access tool can be found in the link in this slide. Just to give you a quick overview of the MOOC, First, we have the introduction and the overview, as like my presentation was part of the introduction, the third part, and then we have the technical topic 1, which is about multi-energy networks, specifically how you can use consimulation and some tools for consimulation and some examples for modeling and analyzing the behavior of multi-energy networks. Then the technical topic 2 is presented, which is about the hardware in the loop validation of modern energy systems. So how can we use the control hardware in the loop and power hardware in the loop simulator to validate concepts and algorithms and equipment for modern energy systems. The technical topic 3, it's about geographically distributed real-time experiments for validating multi-energy systems. So we will see actually the main one or the main contribution of this project, like the interconnection of multiple laboratories for delivering real-time experiments. And finally, we have the technical topic 4 about the designing and documentation of complex test system setups, because when multiple laboratories are involved, it's very crucial and important to design and document the tests that will be carried out, or for example, for future replication of those experiments, or for transferring the knowledge to another laboratory. And in the frame of ERIGrid, we have developed such ways of documenting those complex test systems setups. And the last one will be about industry's opinion and how all those tools that developed in the frame of ERIGrid can be utilized from the industry. Thank you very much for attending this course. My name again is Alex Contu, and here you can find the contact information. Please, if you have any questions, do not hesitate to contact me.